We're going to now build into our spreadsheet an abundance estimator for each species at each site. And we're going to be using the parameters that Jed mentioned, the maximum density per hectare, the minimum habitat required for the species to occur at a site, and the sensitivity score. And to help us get a better feel for how these parameters shape the distribution, we've let cells U21 through U23 represent those three parameters. And we've parameterized this with species number 1. So species number 1 requires 2 hectares minimally to occur at a site. Its maximum density is 0.5 and its sensitivity is 0.05. And this is species 1's distribution model. So you can see the minimum establishes where the curve can begin to rise. That's along the x-axis. So the x-axis provides us with the habitat amount occurring at the site, and the y-axis is the density. The maximum density establishes the ultimate, the highest density that that species can attain, and the sensitivity score indicates how fast we climb from 0 to the maximum. So for example, if we change these a little tiny bit, so let's assume that the maximum density was 1, then notice that the graphic changed automatically, the axes, and so now we climb from 0 to 1, and the sensitivity is key because it tells us how fast we get there. If we set this to a higher number, we get there faster, and if we set it to a smaller number, we get there more slowly. This is critical from a reserve design perspective because if you purchased a reserve and included a reserve that had 80 hectares of habitat, you would be including individuals. This population can have 1 individual per hectare. So you'd be getting 80 individuals. However, if this parcel contained 40 hectares, then 40 hectares we would have 0.8 density of individuals per hectare. 0.8 individuals in 40 hectares is 32 individuals, and that actually can be a significant difference in terms of whether you think this population is viable or not. So Jed walked through these equations, and our task now is to enter that formula that you went through in lecture into the grid in cells S10 down and through all of the sites and all of the species. And let me move our graphic down. The number of individuals we expect is going to be the amount of habitat times the density, right? And the density, though, is going to be tempered by this function that controls the density as a function of the z-score and the habitat amount. So let's enter these in. We need to enter an equation for species that require habitat X and a species that require habitat Y. Let's start with species 1. It requires habitat X, and we're dealing with site A. So this equation, the number of individuals we expect of species 1 in site A is the amount of habitat X in site A times the maximum density for species 1 times the term 1 minus EXP, the negative of the sensitivity score, times the habitat amount. And we'll close the parentheses and close the parentheses again. this will give us the number of individuals we expect at Site A for species 1 given its characteristics. But we know that not all of these species are present, even though they should be. So for example, species 1 requires 2 units of habitat, 2 hectares of habitat, and it does not occur on Site G, even though there are 75 hectares of habitat present. Now, why would that be? There can be any number of reasons why you might expect that species to be there, but it's not. It could be, perhaps, that the habitat is newly created and it just has not been yet colonized. It could be that there's an invasive species that's present and it is out competing our target species, and so our target species is no longer present even though the habitat is there. It could be that the location of that particular site is such that it's at the edge of species 1's range and it has not been colonized and has a little bit different distribution pattern than what's governed exactly by these parameters. So it's not perfect, it's not guaranteed, and to help us to eliminate that problem, we're going to multiply this term by the presence or absence of that species in that particular site. So I'm going to just multiply this by cell G10. Hopefully that makes some sense. Now if we're going to use this equation and copy it over so that it applies to all of our sites and the species, keeping the species characteristics the same, we're going to need to pay careful attention to how we anchor these cell references. As we pull this equation over, we want the reference to the maximum density per hectare and the z-score to stay in column C and column E. So those need an anchoring above for the columns themselves. So we're going to put a dollar sign in front of the C for C10, and we're going to put a dollar sign in front of the E for cell E11. Now in terms of row, as we copy this formula down, we don't want to pull this equation or this reference down or up. We want to stick with row 27. So for the references to the habitat area, we're going to anchor row 27. And that should give us the number of individuals that we expect of species 1, and if we copy that through, that will give us the number that we expect in each of these different sites. And as you can see, we end up with 0 in cell Y10 represents site G because we know that the site was unoccupied according to our data. This formula should work for all of the species that require habitat X. So we'll copy this and we'll paste it in to row 14, row 15, row 16, and row 18. Now let's do the same for the species that require habitat Y. Put your video on pause and enter those equations, and I'll visit with you as soon as you're done. The fastest way for us to enter that equation for the species that require habitat Y is to simply copy the equation for the species that use habitat X and then adjust them. And the simple adjustment is going to be to move the habitat reference down to habitat Y. And then copy those through. So here you have your best guess at the number of individuals that might be conserved in each and every site if they are conserved, given what you know about the current species distribution and given what you know about these species' habitat requirements. So how do we summarize these results? Well, here we need to summarize the size of the population that's conserved given our choice matrix. So here we have our choice matrix in row 30, and we want to count the number of individuals that we think will be conserved given this choice. How would you do that? Yep, it's going to be the sum product function one more time. This time for species 1, our array is going to be our choice array, and array 2 will be the abundance of species 1 across all of our 8 different sites. So by choosing sites B, C, and E, we think that we may have an opportunity of conserving 223 individuals of species number 1. Go ahead and fill in the other remaining 10 species, and then we'll come back and chat about our results. Hopefully you've just used the sum product function in the same way we did species 1. And I'll just click on cell L4 and we'll double check the reference for species number 8, the population size of species number 8. So that would be the sum product of our choice matrix times the number of individuals in each of the different habitats that we've conserved. For this choice matrix, we chose B, C, and E, so our result would be 237 plus 2029 plus 0. And that gives us 2,267. How do we choose our sites using abundance as a criteria? Well, this brings into all kinds of interesting options. The first and easiest one might be just to simply sum the total number of individuals that are present regardless of which species, and we'll do that in cells S20 over through cell Z20. So if we used abundance as our criteria, then we might just look for the site that will hold the most numbers of individuals. We would start with site C, and we would see that we have 7 species conserved. Remember, we still need all species conserved. Our next site would be site A, and that gets us to 9 species conserved. And our next site would be site D. That still does not get us anywhere because we're still at 9 species conserved. That means we need to include site B as well. And there we have a solution where we've tried to maximize the abundance of individuals across all of our species. So let's copy this solution and we'll paste it into cell S6. There's no shortage of discussion that can happen with this spreadsheet exercise because you can see that there are lots of different solutions and they depend on what criteria you set out to use. In terms of abundance, however, we may be interested in simply choosing the site that's going to conserve the largest number of individuals. However, we could take it another step further and we could say, we want to protect at least a population size of 100 individuals across 3 different sites, and that would give us some replication, some life insurance, so to speak, in case one of those sites has a bad year. And we would then be protecting those large enough populations across multiple sites. And we may also be interested in conserving multiple species or communities that may interact with each other. So this problem gets deep very quickly, and these are things that we'll be discussing more in the sandbox. Now, before I close, I want to leave you with this other question here, and we'll head back up to species number 1, and why is it not present on Site G? Species number 1 requires 2 hectares of habitat X, and Site G has 75 hectares of habitat X. Now, what might be causing this species to be absent? We went through this a little bit before, but there's another very good reason that has to do with the arrangement of habitats on the landscape.